Today I plan to sort of split the lecture into two pieces. The first half is going to be devoted to discussing the two-point estimate for SLE, which was first derived by Vincent Bofara in getting the Hausdorff dimension. I haven't been any place where actually it was really presented, and this is actually a very important estimate, and actually generalizing is important. So I think giving at least an idea of the proof, it's actually somewhat complicated, is a good idea. And in the second half of the talk, I will start the motivation to natural parameterization and length and show how looking at this led to the questions I was discussing in the second lecture. And then tomorrow will be a much more formal discussion of the rigorous theory of the natural parameterization. So, mind you, what the two-point estimate, what I mean by the two-point estimate, so I mentioned last time, so I have a domain D that's just a bounded domain, bounded away from the real line. Take 2 points in here and ask what's the probability that, well, I can use either conformal radius or distance. I'll use distance this time. Distance from gamma to z is less than or equal to epsilon, and distance from gamma to w is less than or equal to delta. And that's less than or equal to some constant, which might depend on the dimension d, on the domain d. Epsilon to the 2 minus d, delta to the 2 minus d, to the z minus w to the d minus 2. This part is actually, that is critical when using the estimate, but as I mentioned last time near the end, the hard part is not proving it when z and w are close. It's getting the estimate when z and w are of order 1 apart. So I will actually focus today, since I'm not going to give complete details, in the case where z is equal to minus 1 plus I and w equals 1 plus I. And in that case, I don't need to worry about this term. That's of order 1, and that's of order 1. Well, that just becomes a constant, and I have to show an estimate like that. But it does have to be uniform over epsilon and delta. As I said, the first was first done by Vincent. I think he just did the case epsilon equals delta. For some of the things we've been doing, we need epsilon and delta different, was one of the reasons to go into the proof of this. What I'm going to talk about today is part of a paper in preparation with now we all know how I'm going to finish this, right? With my student Brent Furness. You can tell him he's wasting too much time going to summer schools. He's got to be working on this paper. But hopefully this will be available by the end of the summer, but it's not available yet. So we're going to be following this. What? Oh, D is, okay. D is 1 plus kappa over 8, which is the dimension of the path. I got in a habit a long time ago of just using D, because a lot of formulas naturally come in with D. But it's the Hausdorff dimension. And in fact, Bofara's first reason to look at this, also the first reason was to prove the Hausdorff dimension was equal to that. Vendelin actually gave a picture last time, which is sort of the nasty picture in this. One argument that can't work is just wait till you get, say, well, maybe split it into two pieces. One is to get within epsilon of there, and then delta here, and vice versa. And you say, well, let's wait till I get close to W. So that's supposed to be a small disk. And always have fun trying to draw these pictures. Okay, I don't want to quite hit there yet. So suppose I hit the disk around W first. Then I can ask the question, given I hit the disk around W, what's the probability I hit the disk around Z? Well, if I, by SLE, happen to have done this, gotten very close to Z but not hit it, and have this sort of funny topological shape where curves to infinity have to go through here, it could be quite likely that given, so if my curve to W has done this, then it's very likely I'll actually go through Z and I would not pick up this epsilon to the 2 minus D term. Let me tell you the ingredients. We did one of the main ingredients last time. So there are important lemmas about SLE. So one from last time is, I'll just say, so here D is a simply connected domain. And I'm doing SLE from W1 to W2. By the way, if I didn't mention, I should have mentioned, today cap is less than 8. Cap is less than 8 today. So that's and I choose a Z on the in the inside. And I ask, what's the probability that the distance from gamma to Z is less than or equal to, let's say, R times the original distance from Z to the boundary. And for today, I can worry just about R's between 0 and 1/2. And the key is that this is comparable to, with absolute constants, independent of W1, W2, Z, and D, of R to the 2 minus D times but this is the sign of the argument of Z if you think of W1 as being 0 and W2 as being infinity. And you get a power here, which actually isn't so important for us today, except that its positive is very important. All constants can depend on kappa too. All constants can depend on kappa. We will need another similar argument that almost follows from this, but not quite, but can be proved similarly. And that's a boundary one. So let me just draw the picture here. Let me draw 0 there. Let me draw 1 here. And let me draw the disk of radius r about 1. Then, assuming, let's say, r is less than or equal to 1/2, probability SLE hits this half disk is comparable to in this case, r to the for a minus 1. That's it. That's the same thing. So okay. I can prove similarly. This actually, there's a short proof of this in a note of Tom Alberts and Michael Kostrin, but it also appears sort of implicitly in a couple other places. Again, in reality, we won't need anything except that this is a positive constant, so that we have a bound there. Oh, A is 2 over kappa. So A is bigger than a quarter in this lecture. So 4A minus 1 is bigger than 0. Okay. Now, there are a couple other estimates that I haven't mentioned, and since they're going to come up, let me mention them now, because they should be, well, one of them should be in your toolbox at all times when doing this, and that's the Burling estimate. Which is a corollary of something stronger called the Burling projection theorem, but we'll just do the estimate. And I'll just do it by picture. So suppose I have say the unit disk, and then we start at the origin, and I have a little disk of radius r, and I have a curve connecting the disk of radius r to the disk to the circle of radius r to the circle of radius 1, continuous. And probability Brownian motion starting at 0 reaches the unit circle before hitting the curve is less than or equal to a constant r to the 1/2, some absolute constant. The Burling projection theorem, in fact, implies that the minimizer or the maximizer would be just a straight radial line for which r to the 1/2 is the right order of magnitude. Okay. Well, somewhere I want to try to get a picture here that I'm not going to erase, so maybe I'll start here. So implicitly, let me just make them very small right now. We've got two disks, one of radius epsilon, one of radius delta, that I'm trying to get into both of them. And what I'm going to do is consider this I'll use I for the imaginary axis. And one of the facts that we're going to use is the fact that every time I go from z to w, z or w back and forth, if I go from a disk around here to a disk around here, then I've got to go through here. Now, the key fact that we're going to show, basically, or the basic idea is that if I'm going to get close to z, and I'm going to get close to w, basically one of two things happens. Either I get very close to z without getting too close to w, and then I choose to go to w, or I get very close to W without getting too close to Z, then choose to go to Z. What you've got to show doesn't happen is the tennis match, where you get close to W, close to Z, closer to W, closer to Z, closer to W, closer to Z. And you have to actually show that this doesn't happen, or at least is unlikely to happen. So what we're going to do is talk about excursions between Z and W, where the excursions are measured by this line. Actually, a little more detailed than that. Okay. Unfortunately, the topology gets a little tricky here, and one has to be a little careful. So maybe I'll state that sort of I won't prove this. Topological lemma. This is not very difficult, by the way, but it's if you don't start by doing this, you can run into trouble. Okay, so we can define I sub t, which are going to be subsets of I. And what in our mind is, so if let's just go for a while. Just to get one picture here. If the curve is just hit here, what I want IT to be is this line here. The subset, which has the property that when I cut this from the slit domain, I separate W and Z. So that's one nice picture as to what IT should be. So it starts with the whole line. But now, the real properties we want are the following. Well, it's that we want them to be decreasing. So S less than T implies IT is contained in IS. It doesn't change if I'm off the real line. If S is less than T and gamma ST doesn't hit I, actually, it doesn't change. And very importantly is that IT is a crosscut of HT. So I'll remind you, HT is the unbounded component of H minus the curve. So it's the domain that we're living in. It's a crosscut. Crosscut means it's a curve that's inside the domain, but whose endpoints, it's an open curve inside the domain whose endpoints actually are on the boundary. And it separates C and W. And just to be formal on these definitions, we're going to talk about excursions back and forth. So we'll have a sequence of stopping time. So we start with we start with tau 0 equals 0, Q0 equals 0, R0 equals 0. I'll tell you what the R's are. It's equal to 1. I'm sorry. R0 is equal to 1. So this is representing the distance from Z to the boundary of the domain at that time, the distance from W to the boundary of the domain starting at time 1. But here's the inductive step. So if tau j is less than infinity, we let sigma j plus 1 be the first time bigger than that I get closer to Z or closer to W by a factor of 2. So the distance from Z to gamma of t, actually I could just say Z minus gamma t. Z minus gamma t is equal to Qj over 2. So think of Qj as being the distance from the curve at time tau j. So that says I've gotten distance half better. Or I've gotten there. So at this time, I've improved by a factor of 2 on one of the curves, but not the other. And I can't get to the other curve unless I go through, let me write, as a slight abuse, well, let me write ij, super j, for I at time tau j. Once I get to, let's say I get close to Z, I can't now get close to W again unless I go through my crosscut. So this crosscut is required to go through. So I'm going to let tau j plus 1 be the first time after sigma j plus 1 that gamma of t is in this crosscut. Actually, just to be careful, we'll take the closure of the crosscut. So that's an excursion. And I can talk about Z excursions or W excursions. Oh, thank you. Thank you very much. Qj plus 1 equals the distance from gamma at time tau j plus 1 to Z. So now I'm stopping at this time. How close is Z to that? And Rj plus 1 is distance from gamma tau j plus 1 and W. Thank you. Yeah. I super j is I sub. I actually mean I tau j, not I. But in reality, you actually can't. I sigma j is a subset of that, so you actually will hit I sigma j. So you can't. You actually. Oh yeah. Okay. Maybe there should be I sigma j. Okay. Let me. I did this wrong. Okay. J plus 1. Yeah. Okay. Doesn't. Yeah. Right. Okay. That's sorry. That's correct. That's right. Decreasing. That's actually key. It could, because I could have actually hit I a whole bunch of times before. I could hit I before I actually get to this time. So I'm not looking at every time I return back to this interval. I'm waiting till I get close and then return. Yeah. I is always an interval. It may be an unbounded interval. It might be a bounded interval. But it's actually a definition of crosscut implies an interval. The way I said it, crosscut stays in the domain. It's a subset of I. It's a subset of I. It's a subset of the real line that stays in the domain, and whose boundaries are outside the domain. Of I. Okay. The real line moved 90 degrees. Yeah, it's a subset of I. Yeah. Okay. Okay, now something I'm not going to do today is now if you want to get very close to Z and very close to W, there are actually multiple ways of you doing this in terms of how the excursions could occur. So each excursion only drops things by a factor of 2. So especially as epsilon and delta get small, there could be multiple versions of this. So what you start doing is you sum over, combinatorially, sum over all possible excursions, all possible combinations of things that go on, and then you have to give some sort of estimate. Let me just, okay, one comment that is important is that if this is a Z excursion, which means this has dropped by at least a factor of 2, maybe a lot more than a factor of 2, this has dropped by less than a factor of 2. It has not moved up to a factor of 2. So I don't want to do the combinatorics of all of this. What I want to do is give the main estimate that, or at least state the main estimate that you need in order for the combinatorics to work. So this is the key lemma or proposition. There exists a constant and an alpha bigger than 0. Actually, we can give the alpha an explicit alpha, but that's not required or necessary. Such that given gamma up to time tau j, if we've seen the path up to, so this is probably an example. That's probably tau 1, because I did get halfway closer to W there. So given the path up to that time, the probability of a Z excursion with distance, with qj plus 1 less than or equal to r qj. So the probability that I have a Z excursion, and in fact I actually gained a factor of r in this, is less than or equal to a constant r to the 2 minus d. And now this is key, that distance to the alpha. So what it's saying is that, so if this is my target distance, and let's say the path has already gotten pretty close to it. Let's just, okay. It's already gotten pretty close to it. The probability of a Z excursion is bounded by, well, this is going to be the bound of getting that close to Z will already be bounded by this, by the estimate we have. But we also get a factor qj to the alpha. Okay, so among details left out is, once you have this lemma, you can write down the combinatorics and all the possible events. Basically, the farther you play along in the ping pong game, the worse, smaller and smaller the probability it disappears. So here's the probabilistic estimate that needs to be done. And the important idea, or a very important idea, is that a W excursion, or Z excursion, W excursions are symmetric, it's the same thing, has two parts to it. One is you have to do this, and then you have to return to that interval. And we need both of those things, not just one of them, in order to estimate it. Okay, so let me do the picture. I'll just doing the picture here. So here's Z. And let me do a few cases here. So here's case one. This is a case, well, actually, maybe I should have stopped there. Okay. So here's a case where I've gotten close to Z, so this wasn't excursion. So let's assume this were tau j, or gamma tau j. And I'm trying to get there. So in this case, I super j is an unbounded interval. Since ij is an unbounded, so now we have to do a little topology here. Maybe we should imagine this by map. Well, okay. What I want to do is figure out what the, I don't want to get too far away from this picture. Maybe I'll just hang out over here. We need to look at the probability SLE gets within RQJ of Z is comparable to R to the 2 minus D times this sign factor. And in this case, the domain at this point is H at time tau j. And it's gamma tau j infinity. So I've got this. So basically what I added to the 4a minus 1. So what I need to do is figure out what the sign of Z is in this picture. But there was an exercise that unfortunately we didn't get to in the tutorial, but it's very good exercise. When I'm estimating the sign, what I really need to do is estimate the probability Brownian motion hits the two possible directions. So here's the curve. This is the unbounded interval. Note that in this picture, this is one side of the curve from the perspective. So that's what I called A1. And here is A2. And to estimate the sign, I have to find the minimum of the probabilities that Brownian motion gets there. So in order, A2 is clearly the farther away. Brownian motion, in order to hit A2, has to do this. which means that, in particular, we can estimate the sign by the probability of Brownian motion starting at z gets to this line, staying in H. So this is this sign term. Let me just call this S. Yeah? Okay. H tau j, okay. H tau j is the slit domain, just the domain that we're in. And I thought I did it earlier today, but S is just this. So if I have a simply connected domain and two boundary points and an interior point, then there's a well-defined argument of that interior point with respect to those two boundary points. Just map it to the upper half plane. And this is the sign of that angle, the sign of that argument. So if z is in the middle of the absolute middle of the domain, or the middle line, it's equal to 1. When z is very skewed, it goes to 0. So it's the sign of the... But the sign is less than or equal to probability Brownian motion starting at z reaches I without leaving H tau j. And now this is a picture for the Berling estimate, because I know there is part of the boundary of the domain near z. That's what having qj small would be. So this distance is of order 1. This distance is of order q sub j. By the Berling estimate, less than or equal to and therefore, I can stick qj to the 1/2 here. So this here is less than or equal to constant qj to the 4a minus 1 over 2. I really don't care. I just need some positive alpha. So right. So that does it in this case. But the more fun is the bounded situation. So maybe I'll draw one of those bad pictures. See if I can do this. So there's a picture that might have occurred right after a W excursion. Well, actually, okay, I didn't. This one's supposed to be closer than that one. So I'm trying to get here, or I'm trying to get here. In this picture, so this is I sub j. this case, this is a case where this crosscut is actually bounded. And you may note the picture here. Basically, W and Z are not symmetric in this picture. W sort of has, W to reach infinity has to go this way. Z to reach infinity can go that way. Let's look at the signs of the angles in this picture for both Z and W. For W, note that, okay, if you want to justify this, let me actually draw in your picture, let me just draw this curve, a curve here, which goes to infinity. Just to have that in your mind. That's okay, just draw that, just thinking about that. If I think about this curve, that curve goes to infinity, and in order from W to hit the far side of, here's A2. It's hard. Okay. When one talks about boundaries, one's always talking in terms of prime ends. So different sides of lines are different. So this is A2. And this is A1. So here's A1. This is also A1. For this guy here, in order to reach A2, it has to go through this line here. So for this guy, this same estimate works. So from here, the sign of this guy is very small by the Berling estimate, and therefore the probability that SLE wants to come hit here is very small. Now let me blow up this picture a little bit over here. So I'm going to blow up that picture. So here's Z. This is where we want to get to. And there are parts of the curve. Let's see. Let me just blow up. Okay. So what I've done is kind of blow up this right here. Imagining blowing that up right there. So I is over here. This is A1. This is A2. Now, what I know is that distance from Z to boundary H tau j equals qj. So I don't necessarily, let me just assume that A1 is the closer one. So for one of these guys, say A1, the distance is Q1. Qj. Now, the topology is a little tricky. So the way that I want to measure the distance to the other one is find the, okay, let me move this a little farther away in this picture. So A2 is farther away. What I want to do is find the smallest radius about Z so that I can get some curve that stays in the domain that hits CK. I've drawn very simple curves here. I mean, it can be very, very complicated. So the definition, this curve is the shortest curve from Z to A2, where I'm defining shortness by the radius of the curve, of the disk it lies in. Not by the distance of the curve. So it's really by the diameter of the curve, more or less. More or less the diameter of the curve. And there's basically two cases based on what that distance is. So let me call this distance here delta J. And now I split in this case into two cases. So delta J is either less than or equal to square root Qj or bigger than. So square root Qj, of course, is much bigger than Qj. These are small numbers. If delta J is bigger than square root Qj, then that means there's this Qj here, at least square root Qj there. The probability that a Brownian motion starting at Z gets out this distance without hitting this curve is bounded by the Berling estimate. And I've defined this distance to be the best curve staying in this radius to hit A2. So therefore, the probability of hitting A2 is bounded by that. And therefore, probability Brownian motion starting at Z hits A2 without leaving, or let's say hits A2 rather than A1, is less than, in this case, we get square root of Qj to the 1/2 power. So we lose a factor. And then we get exactly the same situation here, where we have, we actually lose, instead of having 4a minus 1 over 2, we get 4a minus 1 over 4. So all of those three cases had the property that we bounded the probability of an excursion by the probability of entering. But that bad picture over here, if these are very close, that's when Qj is less than square root Qj. When delta J is less than square root Qj, when the distance there. But then, in that case, let's look at this picture. So we have this curve. I put those x's on it because that curve is, this curve here is something that's inside the domain. These curves are part of the boundary of the domain, but this is something inside the domain. Now we're going to take our SLE, starting here, and look at the probability first of entering this disk. So let's look at probability. Let's first look at the event. What's the probability SLE gets within R Qj of Z? And that's certainly less than or equal to a constant r to the 2 minus d, because it's actually constant r to the 2 minus d times a sine term. And I'm just going to estimate that sine term by 1. And now we're going to look at the event that that happens. And I'll just say, so here it's going to happen. I'm just doing this to indicate that this curve doesn't care about that dotted line there at all. So that's kind of an ugly, but there is a first time that it, so that's when it gets to that distance, that's the distance r. And let me extend this to a curve to z just by doing that. That does stay in the domain because that was the first time I got within it close to z. Well, the topology of this could be very tricky, but eventually you do have a curve this in this lit domain. You now have a curve that goes between A1 and A2, some combination of these things that stays in this diameter. So now let me draw a picture again. Okay. I'll just draw, this will do for the picture right now. So, and by the way, Vedlin was right. There should be I at this time. So now we're looking at this time right now. And what I know is that I have a curve that's a combination of these things, but basically I have a curve in the domain that goes through the origin, well, the crosscut goes through the origin and separates this interval from infinity. So I eventually have some sort of domain here that looks like this. There's some curve here. That's the pink. I'm going to draw the pink a little bit bigger. And then there's ij, I sigma j. And then I've got something. What I know is that this distance is of order 1. I actually do not have control here. This could actually be really big I. Okay, so no control here. Except that this is no farther down here than 0. So this is bounded by 0 here. No control on the upper guy. But I know that this guy has diameter square root qj at most. And now it's an exercise using, I like to use excursion measure. It's sort of that we have this conformal rectangle we have something of diameter qj, and sort of the worst possible case in some sense is if ij looked like this, the diameter looked like this, and the rest of it came out like this, sort of. Oh, okay, I don't want, okay. But, okay, but I will just say that the Burling estimate basically allows you to estimate that distance. And what you end up showing is that when I take this conformal rectangle and map it to the upper half plane, so let's say this is the tip of my SLE. There's the tip of my SLE. It goes to u sub t, which we can think of as being the 0 for this. Right. That's the idea. So yeah, right. Okay, I should have emphasized that, but yeah, that it's the two-part thing. You have to actually, if you go to z, you can't get back. You can't get back, and that would have been the 30-second version of the talk. And in fact, I only have about 30 more seconds of this version. In this version, this pink gets mapped to something, and this thing gets mapped to something. Like that. And by conformal invariance, using this sort of estimate, we can estimate the, so this is where the SLE is starting, the excursion measure or extremal length or some measure of that, of this with respect to this. And we see that this is sufficiently small, so now we use the boundary estimate. Which is the extra one that I gave. And I won't go through the, and you get a QJ. And then, so as Fedlin said, I'll just say one more time, basically the important thing is that when you talk about these excursions, you can't either if you've already been very close to something, either it's hard to get there or it's hard to get back. And when you finally write the proof, the last time you hit something, there's no excursion there, but that's okay. Yeah. Right. Yeah. So the excursion is two-part. Yeah. That's the key. That's the key. Is the excursion is getting close to there and getting back to the interval. Because there's only one of those. That only happens once in the combinatorics. No, but okay. But what you do is you write all possibilities are all possible things before the last one times the last one. And if you sum over all the possibilities before that, this sort of last one is one factor. In order for what? I mean, I don't mind. Okay, in my arguments, I don't mind having this happen once. Later in the so in other words, if I happen to be in this situation now, if I'm in this situation now, then what I'm basically saying is, at this point, I may get closer to z. I may still have getting closer to z to deal with, but I won't have any more excursions. So all I have left is to talk about how close I get to z. Well, w, okay, maybe I don't understand your question. Well, actually, that was one thing I wasn't going to do, but basically, what you do is just do factors of 2. So, you know, how many, in factors of 2, at which times did you have excursions? And you just sum over all possibilities. What happens is, if you've had many excursions, then they, by definition, they have to be smaller and smaller, because each excursion always takes a factor of 2. So they get smaller and smaller, which means you get more and more terms of this qj to the alpha that added up. And you know, the more excursions you get, the more bad stuff you get, and it just adds up. If it swallows either z or w before one of the events, game's over. It's not getting any closer. Yeah. Yeah, that's yeah. Unless z and w are in the 8, you're not going to get any closer to them. I did want to state one result you get from this. I mean, one of the key things is that what you get is that if you're going to go get close to z and then get close to w, you either get close to z and then close to w, or vice versa. You don't hop back and forth. And in fact, one can prove the existence of a multi-point Green's function. I'll just do the 2 case. So there's a function, and this is in the paper to be with Brent. There's a multipoint GZW so that in fact the limit as epsilon and delta go to 0 in any order that you wish, probability that, in this case we'll use conformal radius, that so we have that probability. That probability is going to 0 at a certain rate. Let's multiply by this to keep it of rate 1. So now it's going to 1. And well, the way we've defined it, this is the same C star I had in the Green's function result, G of ZW. So you actually can get that simultaneously. You can do 2 of them. Yes, it's much stronger, but the main tool in proving this is this. I mean, it's what this is. I mean, I can say sort of what this thing should be. Let's just say what this thing should be. Well, to start off with, this really has 2 separate terms. One which corresponds to hitting z first, then w. And the other one which goes to hitting w, then z, because it's ordered when you hit things. So I really should write, so this Green's function is the sum of 2 things which are not symmetric. Think of this as being the probability SLE goes to z and then goes to w, and this says SLE goes to w and then goes to z. Oh, right. Okay, this is the upper half plane. This is the upper half plane. Oh, this is, okay. Sorry, this is the multipoint SLE, sorry, multipoint SLE kappa Green's function. I'm sorry, yes. And maybe, okay, there's an open problem. Is there a better name for this? because there is confusion. This is not a Brownian. This is an SLE kappa, multi-point SLE kappa Green's function. It's the, and to be precise, for the way I've defined it, for SLE from 0 to infinity in the upper half plane. Well, let me write down an expression, and then I'll just come back to that answer, because the expression will have some of that answer to that question. At the moment, we don't have an explicit form for this, and that's actually maybe a more interesting open problem. Can you give an explicit form for this thing? But we can describe it. So if I take z, so let's look at this guy. Let's look at the one which corresponds to zw. And I'll just do the picture. What this says, what is the probability that SLE goes to z and then goes to w? Well, yesterday we just talked about two-sided radial SLE, which corresponds to chordal SLE conditioned to go through z. So basically, there's a well-defined probability measure which corresponds to chordal SLE going through, conditioned to go through z. With probability 1, that particular thing doesn't hit w. So basically, the probability that I get close to w within delta of w, given that I get close to z, is just given by, well, there's, what I do is the probability I get close to z looks like g of z times c star times epsilon to the 2 minus d. Normalized by that, take the limit, I get a probability measure here. It stays away from there, and then from here, I know, given that, I know what the probability of getting close to w is. And if you thought about this and understood it, you could write down what the formula is, and that's right. The key thing here, there's a tightness argument that's needed to show, and the tightness argument is, again, showing you don't have the ping-pong game going back and forth. So conditioned to get through z, the distance to w is tightly bounded away from 0. That's the way to think about it. Yeah, so of course, there's a probability of any distance that you want has some positive probability, but it's some random, so it doesn't actually get to w, and it, yeah. It's of order constant, right? And it's a random variable with, right. So if you actually want to know, of course, if you want to know the probability that you go to w, you need to know both the distance and whatever sign for term you got. Whatever's remaining at that point. So this is, there's not much more in this argument besides that estimate there, but I don't know any way to justify this without going through this kind of argument. Okay. That's as much as I'm going to say about this. So now I'm going to switch gears and sort of start the introduction heuristics for tomorrow's talk. So now I'm switching gears. So natural parameterization, or sometimes called natural length, either one. I think parameterization is a more natural word, but length takes fewer letters to write. So. And length is pretty natural too, actually. Okay, So we're going to do SLE in the upper half plane. So I assume in the first 2 weeks you had a number of models that scaled to SLE. Actually, my favorite one to think about is one that's still a big open problem, which is to show self-avoiding walk scales to SLE 8/3. But also loop race walk, which is known to, but let's say loop race walk is known to scale to SLE 2. But to be precise, SLE, loop race random walk, if you give it the capacity parameterization, is known to go to SLE 2 with the capacity parameterization. That's a parameterization. But if I've got a discrete random walk, when you do a discrete random walk, what you naturally do is say, it takes time 1 to do this, 1, 1, 1, 1. We have a natural parameterization here. And say, let's do for loop race walk. So for loop race walk, suppose that this was distance n. Okay. Suppose you did loop race walk, so it had radius n. Then the number of steps is like n to the 5/4, result of a Rick Kenyon. So what you would probably do if you want to scale this so that this distance was 1, you've got n to the 5/4 guys here. Here you had time 1, 1, 1, 1. You scale time. So this is scale by 1 over n. We scale time by 1 over n to the 5/4. And what you would expect is to get a limit and the limit should be up to parameterization. In fact, it is SLE in this case. But SLE had to change this time parameterization. So what I should end up with is a parameterization that's effectively well, in the case of loop race walk, a 5/4 dimensional measure on the thing. Things should scale by 5 there. In general, we would expect that the parameterization should be a d-dimensional measure. Let me just say a little bit what that means. So suppose I've done my SLE curve for a while, and I'm going to do a little increment. Now here's gamma t. Let's take gt. And this is gamma t plus delta t. So right now, let's assume I'm using the capacity parameterization, the usual. And by the way, I don't care whether I have factors of 2 or factor of a for the purposes of this talk. Then in the capacity parameterization, the amount of time to traverse this is square root delta. I'm sorry, is delta t. It takes time delta t to do this. In capacity parameterization, it's delta t over here as well. That's one of the beauties of the capacity parameterization, is that the time parameterization is invariant to this. Like the increment in the time is the same over here. Now, that's not what one expects for fractal measures in general. For example, a good example of this is Brownian motion. When you take conformal transformations of Brownian motion, you have to change the time parameterization. That's because Brownian motion is basically a two-dimensional object, and when you blow it up by a factor of 2, you need to blow things up by 2. Well, in this case, by 4, 2 to the 2. So here, if I look at, let me just write, let's call just a letter d for the diameter. So let's just call d for the diameter there. Now, in the capacity parameterization, the amount of diameter there in capacity time delta t is a random variable. Sometimes it's a lot, sometimes it's little. So that's d would be random. But over here, the diameter should be of order root delta t. So in time delta t starting at the origin, the radius tends to be of order root delta t. But basically, what one expects is that if this is a very little piece here, then the diameter over here is gotten up by a blowing up factor. So we expect, in fact, this diameter to also be of the order, okay, let me call this d tilde over here for this time. gt prime times see, we're blowing up by a factor of this, so it's gt prime to the d. Okay, now I've been sloppy here, and that's actually in a number of ways, but one of the key things is that I'm really looking at the increment of the curve here, but gt is not smooth here. So it's not really the case that there's a single value of the derivative there. And I'm just assuming for the moment that there is, but there's not. Or if I go this direction, I can say that d should be about 1 over gt prime times d tilde to the d, or ft prime times d tilde. So that's the blow up you expect for if you really have a d-dimensional object. The derivative? Well, I'd love to do it on the curve, but that doesn't make any sense. Well, okay. It's okay, but it's the blow-up factor of this ball. So what I really want is sort of the typical value of the derivative on this ball, which is a little bit away from the curve. Of course, I mean, the picture could be much, much worse than this. But the idea is basically I've got this picture. Maybe I'll take the derivative there, which makes sense, and use that. I'm waving my hands. Ah, okay. Good. Okay. When you scale like I did here, one actually expects that when you scale to get a d-dimensional curve, you actually expect to produce a d-dimensional measure on that curve. Excuse me. Okay, I forgot to say something. Okay, thank you. Okay, I meant. Yeah, no, okay, no. I did miswrite something. So, okay, everyone erase their mind for about 3 minutes. And let me rewrite this. So what I meant to say is, let's consider how much time it took to traverse this in the natural parameterization, in the d-dimensional length. So we have, so let me let, so, well, I'm going to use this later, so I'll do this now. So theta t is time to traverse, time to traverse gamma t, t plus delta t in natural parameterization. So I'm just going to put, so that's over here, it takes me time. I'm just going to call that delta theta. It takes me that much time over there. Over here, it takes me some other amount of time, so I'll call it delta theta tilde. So what I'm going to say is, I do not expect this and this to be the same. This is what I expect to scale. And what I expect is that, thank you, is that delta theta tilde should be like gt prime times delta to the d times delta theta. That's what I meant to write. I'm sorry. Yeah, forget, but yeah, okay, yeah, let's, right. I'm sorry, yeah, I'm sorry. I wrote the wrong thing. Okay, that's what I meant to write. But I also meant to write the, okay. And the other thing I wanted to write, okay, is that I would expect delta theta tilde to look like, okay, let me still call this d tilde. I'll still call it, okay. Should look like d tilde to the dth power. So if I've got a d-dimensional measure, something of diameter d tilde should look like this. So over here, this takes square root delta t time in capacity. And I'm just saying this should be, diameter is square root delta t to the d in natural. Yeah, I apologize for what I said before. So that's what it should be. So it's delta t. So that gives you the amount of time here. And so and my claim here is that this should be square root delta t to the d times the derivative in this direction. That should scale. So if this would take me square root delta t time in the natural parameterization, then we more or less say this here in the natural parameterization. And what I do is, okay, I haven't plugged in a point yet, but let me just plug in a typical point here. This diameter is like square root delta t, so let me put in I square root delta t as a typical point. So So the idea of this is to give the following intuitive view, just intuitive guess, that roughly speaking, the amount of time of, I'll say, natural time to traverse t plus gamma t to gamma t plus delta t. And this is the capacity, right? So this is, yeah, so, right. So right now, gamma is parameterized in capacity. So that takes delta t time in capacity. In natural time, and of course, this is really fudging constants and things like this incredibly much. But it's just sort of a first round guess of the order of magnitude. And this leads to a conjecture which is still open, is that I could define theta t to be the limit as n goes to infinity, the sum j less than tn ft prime of I over 1 over root n. So here I'm using delta t equals 1 over n in this expression to the d, and then I have a delta t, square root delta t to the d over 2, which would be an n to the minus d over 2. Okay, when I make this conjecture, just a couple of things. First thing, whatever this natural parameterization is, it sorry. Sum j over n, I think is. When I talk about natural parameterization or anything like that, it's always up to a multiplicative constant. I can always change my time unit. So I'm not worried about exactly which constant I come out with this. I didn't even bother to tell you what kind of limit it is because I don't know how to prove it in any sense right now. You might also, instead of taking n, you might want to go 2 to the n's, not go along a geometry. I mean, there's lots of things you could do to this conjecture. But it does lead one to look at what happens when you have something like this. And let me tell you that it was looking at this and trying to analyze this that motivated the detailed discussion in the second lecture. So this is really an example from that. So for instance, let's take the expected value of this. So, okay, now let me change this for a second, and let's just take the let's just take the expected value of the sum, the expected value of the right-hand side. And maybe let's just do it at t equal 1. So that's the, and let's not worry about the, okay. Let's not worry about the limit either. Let's just take the, okay, the expected value of this. That's a D. It doesn't really look much like a D. And that's in the form of the kind of things we were doing on the second day. Here, this is an example where what I called lambda is equal to D. And this happens to be a particularly nice example. Now I want to make sure I just get rid of So in this particular example, lambda equals D. Now we're using lecture 2. Lecture 2, I had R, lambda, and C. Or R lambda zeta, I guess. R lambda zeta. And if I want lambda equals D, one can check that R equals 1 and zeta equals 2 minus D. And as I say, today kappa is less than 8. There was an R critical, which was 2a plus a half. And what I said was all that analysis there required R to be less than R critical. For kappa less than 8, if I stick in R equals 1, it is less than R critical. So in fact, we can actually work out and at this point, because I'm running short of time, I just like to sort of state the results that one gets. So one gets that. So expectation ft prime of I to the D is like t to the D over 2 minus 1. I'll leave it to you to check that that's the right thing, so everything's consistent. This expectation tends to be of order 1. But that detailed analysis gave more than just the expected value, but it also tells you the typical value of it, of the derivative when you weight by that. So the expectation is carried on an event where ft prime, well, I'll do, okay, I've now converted this into this way, okay. D minus 3 halves. So I know the typical value of the derivative. And the probability of the event of this event. So this is an exceptional event. And the probability of the event is just n to the, well, that's my definition of alpha, is n to the minus alpha. But it satisfies this. I mean, just I mean, okay, there's nothing in this statement. It just says if this is where it's carried, then on this event, the dth power is equal to this. And the probability is n to the minus alpha. Therefore, its expectation is n to the minus alpha times that. And that lets you solve. So then you get that 1 minus alpha equals d over 2 minus d. And I want to at least explain these things. That will be one of my things I'll say in a couple of minutes that you just ruined the punchline. That's it. But then I get to say a lot more than just that. Okay. I get to, yeah. So what I get is that if you think about this, what this says is the limiting measure so when I say limiting measure, I'm not worrying about whether it exists at the moment, but would be suppose I take this limit here and think of this increasing function as giving me a measure. Is supported on a set. Okay, limiting measure, actually, okay, here's an important point. I'm sorry, okay. So we have this guy here. It's going to give a measure on the curve. So we're going to have a measure on the set gamma t. But this curve is an image of 0, 1. Let's say it's an image of 0, 1. So I also have a measure on the interval. So this is, I'll call this the measure on the time space and the measure on the space. I don't know. But we have a measure here, and we have a measure living here. Right. But of course you can't do that. Lives on a set of times of dimension 1 minus alpha. So, I mean, it's supported on those points, so where it's supported on this event. This event has probability n to the minus alpha. So the dimension of this set looks like n to the 1 minus alpha. But right, so you can write it as a, okay, you can write it as a, I mean, you have to be careful about this, but you can you need to get your sub-power functions out and things like this. Okay, so there is, yeah, okay, no. I mean, here's two very rigorous statements. There's a set of dimension that which has measure 0 off of it, and any set of smaller dimension has 0 measure. Those are two very good rigorous statements that are correct. Very precise statements. And not really, okay, exactly what this, I'm trying not to say exactly what this set of looks like. Okay. No, it's not a compact set. You may be able to write it as a countable union of compact sets. But actually, okay, okay, well, I'm going to go a little bit longer today. I'm sorry. Lunch goes a long time, don't worry. Set of times of this dimension. But the image has dimension. Well, there's a couple ways of computing it, but basically, the set of times we covered by n to the 1 minus alpha things of size 1 over n. If I want to know what they look like on space, these things of size n are blown up. They're blown up by the factor of the derivative. But if you think about what we're doing, and do the jump ahead, it actually, the image has dimension d in this case. Now, as Vendelin said, and it's an important point of this when you realize all these things, this theta t is something which should be growing on a set of times of dimension strictly less than 1, which means that it's a singular function. And in fact, so the natural parameterization and the capacity parameterization are singular with respect to each other. You can't differentiate. It's no nice time change. They will turn out to be continuous with respect to each other, but singular. Also, when you go to the limit, the set of points that it lives on, here I said something that happened at a particular n, but you actually look at the set of points such that f set of t's, such that ft prime of iy looks, and here I have to double squiggle, which means that I need to pull out my sub-power functions in. Y okay, n to the d minus 3 halves is 1 over root n to the whatever. Okay, just whatever's right over there. But you actually get that there are actually points. So something which may be a bit, these exceptions, these are points where the derivative is greater than usual, but it's consistently greater. It follows the same exponent all the way down. There are also points, really, really exceptional points where it oscillates between exponents, but they're significantly less. But here we have this. Let me just finish today by saying this. As I've stated here, it's not rigorous because one needs to get second moments to take a limit. I don't know how to do that. However, there's not independence. You can talk about the correlations. They're not independent. The ft prime depends on the entire path up to time t. That you can do. And if you've got two different times, you can compare two different times by looking at one time and an independent composition map. And that sort of stuff you can do. And I'll just say that I don't know how to get the right second moment estimates for this, but I can take a submeasure of this. When I say a submeasure, I could put an indicator function of some event. so that the limit still has positive, so still is positive. And this event, if you go back to lecture 2, I was talking about some event of curves, some e there. That's where that comes from, is putting on this. And what I can prove is subsequential limits for this. And I just want to state, what I really want to state here is, using that technology, one can actually produce from this a measure on the curve that's d-dimensional. Once one has a curve on the measure on the curve that's d-dimensional, basically that gives you the lower bound for Hausdorff dimension. So this argument gives an alternative proof to the more forward, straightforward modulo one hard estimate way that Pafara got the Hausdorff dimension. This doesn't need to use Pafara's that 2-point estimate. It needs to do 2-point things for the reverse flow, and it's done differently. But okay, so that's what I'm going to stop here. I will finally stop here. Tomorrow, what I plan on doing is discussing a rigorous notion of natural parameterization, and I'll start from there. Okay.